So let's go ahead and do fluorine. And you're going to need to be on that page 265 for the electron negativity numbers. So you're going to get your chemical kit. And because this is your molecule, so when you have a molecule like this, you have two halogens. Remember, the halogen is going to be green. Now, can you close the door for me? You have a fluorine and a fluorine. Now, going back to the previous chapters that we've done, you have a fluorine. Let's make this a little bigger. And that way we can make that right there. Okay, how many valence electrons does fluorine have? Remember, you're going to count from left to right. First of all, how many valence electrons can you have, period, around any element? 8. And fluorine is in the halogen group, so how many dots does it have?
7.
It has 7. So you're going to have 1, 2, 3, 4, 5, 6, 7. Okay, and that goes for the other side as well. 1, 2, 3, 4, 5, 6, 7. Now, I always leave the empty spaces next to each other because this is where they're going to bond. Now, is this an ionic bond or is it a covalent bond?
Covalent.
It's covalent because you have two nonmetals, right? So whenever you have two nonmetals together, this is a covalent bond. Now, you don't have to write that on the paper. I'm just refreshing your memory. When you have a covalent bond, that means that they share electrons. Okay, an ionic bond, they transfer. So because they share, this dot and that dot are going to share a bond. So in this one bond, this one small bond, that means you have a dot on this side and a dot on this side, and these two are sharing. Okay, we see that? All right, so now what is my shape for that particular... okay, so this is gonna, you can either draw it in, or you can write the F bonds with F, okay? So you can either draw it or you can put the elements on there. But don't forget to put the bond in there. Each bond has one electron on each side of that bond, okay? Now, for the electron negativity, you're going to look on that page 265. So look under fluorine, and you should have a 2, 3 number on that element. So look at fluorine. What's my number? Mijo, you need to unplug. No one should be plugged right now during the lesson. Okay? What's the number on that periodic table? On that electron negativity? 3.98. Okay, so that means this fluorine has 3.98, and this fluorine has 3.98, and you're having a pool on each side. That electron negativity is the force it takes, is the force it's using to break the bond. Okay, so here you have 3.98, and then you have 3.98. It's like they're playing a tug of war. Is it going to move? No, because it's the same amount, right? Now, remember that when you have a single bond, it's going to be easier to break that bond than when you have something like a triple or a double bond. Okay? That's why your simple sugars, like something like carbon dioxide, it's a single bond. So it breaks easily. Like your natural sugars, vegetables, things like that, it's gonna be easier to break. When you have something like breads and like your candy, your complex sugars, your Doritos, you're gonna have more of these fatty molecules. They have triple bonds and double bonds. It's gonna take a lot more force for it to break. Okay, so which one is it gonna be easier to digest?
Simple sugar.
The simple sugar, right? Okay, and this is gonna be a stronger bond. So it takes a lot more work. You have to exercise a lot more to break those bonds apart. Okay? So you're going to have that 3.98 minus 3.98, because that's your bond. What does that give you? 0. Very good. So whenever you have that, and you're looking at that molecule, that bond, you have that 3.98 pulling against that 3.98. So it's not moving at all. You have a zero movement. That is a non-polar bond because it's equal. You have the equal amount of force on each side. Okay? What if I had something else like an oxygen and a hydrogen? Would those be different? Yeah, what's your number for oxygen? 3.44. And then minus that 3.98 is going to give you an actual number, right? So that means one is going to be pulling the other. One's going to have more force than the other. So because it's unequal, that would be polar, okay? But now, in this particular case, you have only one bond in the whole molecule. So the whole molecule is also non-polar because you have an equal pull. Okay, we see that? Pick a different compound on your lab that has more than one bond, and I can show you what I mean by molecule. Yep. Pick one on your page that you'd like for me to do. Another example. Pick one that's on your paper. CH3Cl. Okay, let's do that one. CH3Cl is actually right here. Okay, and let's go ahead and take a picture of that. Hold on. Okay, so here's a picture of my Cl. Can you see it in black? Let me try red. Here's Cl. Here's hydrogen. Here's another hydrogen. Back here, there's another hydrogen. And right here, we have carbon, right? That's my CH3Cl. Now, is this a covalent bond? Is it an ionic bond? What type of bond is this? Can we see the red? Or do we need that to be in black? Okay. It's covalent, so that means these are going to share. So I have a dot here and a dot here. These are sharing electrons. I have a dot with the carbon and I have a dot with hydrogen. These are sharing because carbon has 4 dots. So 1, 2, 3, 4. And each hydrogen has 1 dot. So they're sharing. Now chlorine has how many dots? Yep, very good. So the 1 dot from carbon and the 1 dot from chlorine, they're sharing right here. Okay? Now, what's my electron negativity? First of all, what's my shape here? What's my shape when I have 4 on each side? Yep, very good. That is a tetrahedral. Okay? Now, you will be given like a picture on the test, and they'll ask you what's the shape. And so you have to look at the whole thing. You know, is it a tetrahedral? Is it something that's, like this is linear as well, okay? You can have more than one bond. This is bent, okay? And so those are the ones that are on page 29 that we did before break, all right? Okay, so now what's my electron negativity for hydrogen? Look at your page 265. What's my electron negativity? 2.20. Now remember here, part of your objective is not only to see what the shape is, but what's going on in the shape, okay? And these numbers are going to tell you what's going on in there. What's my number for carbon? 2.55. So 2.55 is in the middle. And what's my number for chlorine? 3.16. So I have 3.16 right there. Okay? Which one has the stronger force out of all of these? The chlorine. So when this is spinning, I know that when you have a molecule like this, and can you see what's happening? Is it moving for you? No. You can see the shape, but you can't see what's going on. But by the number that's on the table, that's what's going to tell you which one's going to have more strength. You're going to have more force, so the chlorine's going to be pulling all of these hydrogens like that. Okay, so while this molecule is moving in motion, the chlorine will be the one who's winning that tug of war. Okay? So it's going to be going in this direction. Right? So now, that whole molecule, this is the whole molecule. Is this polar or non-polar? Polar. It's polar because it's unequal. So the whole molecule is polar. Very good. Now, just between the carbon and hydrogen, that means you're just taking this black molecule and this white molecule. Is this polar or non-polar? Remember, non-polar means it's equal, and polar means it's unequal. Sorry, I still have my cold. Okay, so is this polar or non-polar? Polar. This is polar because it's not equal, right? So between carbon and hydrogen, that's polar. Now, what about carbon and chlorine? It's still polar because for carbon and hydrogen, you have the 2.55 minus the 2.20, and it's giving you 0.35, right? And for the carbon and the chlorine, let me do this over here. The carbon is still 2.55, but the chlorine is 3.16. What is that going to give me? It's giving you a 0.61. So the fact that you don't have a zero force, that means it's polar because it's unequal. Okay? Huh? On the calculate electronegativity. Huh? It's because I put it down here. Okay. Okay. So now, let's go ahead and move that. Can I clear that? Or can we just squeeze it on this side? Here, let's. Okay. So, huh?
He's asking how do you know subtract.
Because you're going to take the actual elements.
Well, I know, like, but how do you know which elements to subtract from each element?
Because it's giving you, when you do the molecule, it's giving you the elements. Right? Because you had, here, let me draw over here because I ran out of space. You had carbon, you had
Like,
hydrogen.
The ones that don't give it to you, like this one did. I think.
Well, all of them are giving it to you because it's on the left.
Well, I understand, but like, whenever we're doing the calculate, how do you know which one's on top and which one's on the bottom?
You're just going to take the higher electron negativity minus the smaller electron negativity. Okay? Because they're both in the same bond. Okay? So now the whole molecule was polar and the bonds were polar, right? But what could we do to make it non-polar? You had carbon, hydrogen, 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 and a chlorine. What could we have done?
Change the chlorine to hydrogen.
Yep, you could change the chlorine to hydrogen. Now they would all be 2.20, 2.20, 2.20, and 2.20. That means you have the same pull on every single side. And instead of this being green, it would be white as well. So every single pull would be the same. So is that carbon going to move? If I changed this green to a white right here on this molecule, it's not going to move because you have the same force pulling in every direction. So is the bond still polar?
Yes.
Yes, because carbon and hydrogen are not equal, right? But when you look at the entire molecule, carbon's not going to move, right? Because you have the same pull on every single side. So here, instead of being polar, it would have been non-polar because you would have an equal pull on every direction. We see that? Okay? Yes? Okay, now can you see why you need to do the molecules? I saw people earlier today doing the lab without doing the molecules. I will not give you credit for that. The whole point of this lab is for you to actually look at the shape. So you can share, like 2-3 people can work on one of these. I would do the shapes first and the electron negativity because you can't take these home. We see that? Okay, what questions do we have so far? Are we sure?
How would you know which ones are in the middle?
How do you know which ones are what?
Like the one where it was like CH3Cl.
Mm-hmm.
How would you know that the carbon's in the middle?
Because when you're doing that's a good question. In case that's too far away. Let's go ahead and put that on a piece of paper. That when you're doing the molecule, here I have fluorine and I have fluorine. These two dots are sharing. That's what that bond is because it's a covalent bond. Now, what is that shape? Look on that page 29 for all your shapes. It's linear. Very good. So you're going to write in that box linear. Let's move this to the side. Okay, when you're doing the carbon, you're going to look at the valence electrons, and you have 4 dots. So you have 1, 2, 3, 4. When you had hydrogen, hydrogen has how many dots? It only has 1. Okay, so that's going to tell you how many bonds you have. When you're doing the actual molecule, it's going to either have, for example, hydrogen has only 1 spot where you can put the dot, the actual bond. Where if I get an oxygen, I'm going to have 2 holes. You see this? So instead of using a small bond, you need to use a longer bond, because you see here how 1 can fit here. That means you're going to have to put, instead of this one, you have to put a longer bond so it can bend. You see how it's going from the carbon again to the oxygen? And so instead, let's do a different, that carbon to the oxygen, instead of having only 1 bond, is going to have 2 bonds. You see how you have this double bond here? Because you have 2 spots. And that's the whole point of actually doing the molecules. The molecules is going to have the empty spaces for you, so you can do the bonds. Okay? That's going to happen also, like for nitrogen. You're going to have enough spots to do 3 bonds. So this is going to be a triple bond. This is a double bond right here. And then these are single bonds. Okay, we see that? Good question. Anybody else? Are we sure?
Bonds higher than triple?
The triple bonds are higher. They're going to be stronger. So they're going to be harder to break.
Is there like quadruple bonds or no?
No. You're going to have just triple, yeah. Okay? So you can have a single bond, a double bond, or a triple bond. All right? Good job. All right, go ahead and grab a kit. And I would do the shapes first. I'm going to go ahead and leave